This is the recorded version of the Optimetrics Getting Started guide. Before covering this tutorial, it is recommended that the user be familiar with the waveguide T-junction Getting Started material by first working through that problem. This Optimetrics Getting Started problem will build on the T-junction created during the previous Getting Started session. If you have the hard copy Optimetrics Getting Started guide, you may wish to follow along at this time. While the Optimetrics module allows the user to perform a variety of functions including parametric analysis, optimization, sensitivity analysis, tuning, and statistical analysis, we will concentrate on parametric analysis and optimization to demonstrate the basic use of this tool. As mentioned previously, this exercise builds on the waveguide T-junction problem created in the basic HFSS Getting Started guide. The T-junction is a basic 3-port waveguide with a septum to control the power split between ports 2 and 3, when the device is driven with a signal at port 1. We will use the Optimetrics module to determine the position of the septum that will provide a 2-to-1 power split between ports 2 and 3. Before we begin, let's first open the previously solved project using the File Open command in HFSS 9. Locate the t.hfss project and click Open. Once the project has been opened, we'll want to use the File Save As command to save the project to a different name so that we don't lose the original project. We'll save the file as OptimT in the File Name text box and click Save. There's one last setup item to take care of before we begin. During the previous exercise, a frequency sweep was specified. However, we will focus on optimizing the device at the solution frequency of 10 GHz and do not need to run a frequency sweep. Therefore, we'll highlight sweep 1 in the project tree and delete it. With this change, we're now ready to set up a parametric analysis. If you're following along with the hard copy manual, you should be ready to begin with Chapter 3. We begin by adding a parametric sweep of the variable offset that was defined in the previous problem setup. This is the variable we use to define and change the location of the septum during the initial problem setup. We add this sweep by right-clicking on the Optimetrics entry in the project tree and selecting Add and then Parametric. The Setup Sweep Analysis dialog box appears, and we begin by clicking on Add in the Sweep's Definition tab. This brings up the Add Edit Sweep dialog, with the variable offset selected by default since it is the only variable specified in the problem. We will stick with the default linear step and specify values of 0 inches, 1 inch, and 0.1 inches for the start, stop, and step size respectively. After setting up the parameters, we click Add, and the variable sweep is loaded into the description panel. We could add numerous variables and sweeps if desired at this point. We'll click OK and return to the Setup Sweep Analysis dialog and continue with the parametric sweep setup. The sweep definition is now loaded in the top half of the window. If we select the Table tab, you can see the individual steps in the sweep and make modifications to them if we choose. Moving to the General tab, we want to enable the Save Fields option so that we can view the field solutions at each individual septum location. This option should be used carefully since a large number of saved field solutions will require a lot of disk space to store. Finally, we want to specify some solution quantities to calculate at each variable step. Clicking on the Calculations tab and selecting Add will load in a blank solution quantity based on the last adaptive solution. We now select Edit Calculation to bring up the Output Variables dialog so that we can define the calculation of interest. Since we are interested in power ratios, we'll use a mag_s squared calculation. First we add a name, power11, in the name field. Then we verify the category is S parameters, and we have S11 selected in the quantity list, and we'll select mag for magnitude in the function list. We click Insert Quantity into Expression to load the quantity into the expression evaluator. And on the keyboard, type in the multiplication symbol, and then insert quantity into expression again to give us the magnitude squared calculation. And click Add to load this into the output variables. We'll do this 2 more times for power21 and power31, and using S21 and S31 respectively in the calculation. When we're finished, all 3 output variable quantities are listed for calculation at the 10 GHz frequency of interest. Now we add 2 more line items to the Calculations tab and select under the Calculations text edit box the appropriate quantity. We click OK, and this completes the parametric setup of the problem. And you can see the parametric setup is now visible in the project tree under the Optimetrics folder. The solution is run by right-clicking the parametric setup entry in the project tree and selecting Analyze. We'll jump ahead to the solution, but we should note that the Optimetrics module has access to the 0 and the 0.2 steps run from the basic solution and will not resolve these steps. Now that the solution process is complete, we can look at the results of the parametric analysis in a variety of ways. The first thing we want to do is compare the results of the calculated output variables we set up, power11, power21, and power31. We do this by right-clicking on the Results folder in the project tree. Select Create Report, and keep the modal S parameters and rectangular plot defaults. In the Traces dialog, we select S11, hold the Control key down and select S21 and S31. We verify the Use Primary Sweep setting in the X tab, and we move on to the Sweep tab. In the Sweep tab, we select Sweep Design and Project Variables, since we want to plot against the value of offset. We then switch the primary sweep to offset by clicking and selecting with the pull-down menu. We're now ready to add trace and click Done. And we should see our S parameter plot. Just a little note here, you can click on the trace and then right-click on it and select Properties. And here you get a Trace Properties dialog that you can select things like the line, style, the scaling. We'll turn on the Show Symbols on all traces and scroll the symbol drawing down to every 1 data point and click OK. And there you can see the symbols on the traces. Now we'll dismiss this plot and create a new one to review the power distribution that we calculated during the solution process. Again, we use the Create Report function by clicking on the Results folder in the project tree. This time we change the category to Output Variables from S parameters. And there are our 3 quantities. we'll select power 1, 1, power 2, 1, and power 3, 1, and proceed through the rest of the setup in the same fashion as the previous plot. Again, we have to remember to change the primary sweep to the value of offset. After adding trace and clicking on Done, we get a plot of the three quantities of interest. Notice that the point on the far left of the plot is the location where the septum is centered in the junction and the power is divided between ports 2 and 3 evenly. As the offset increases, the septum moves closer to port 2, which allows more power to flow to port 3, and a correspondingly smaller amount to flow to port 2, as expected. Using the data marker, we can see that the offset value of 0.1 allows roughly twice as much power to port 3 than to port 2. Select it again here, and there you can see the marker shows a value of y of 0.65. This will be the point at which we will start our optimization in the next section. As a note, you can also review these results by right-clicking Parametric Analysis in the project tree and selecting View Analysis Results. And there are all three individual traces. Before we move on to the optimization process, we can look at the field solution and see how it varies with septum position. First, we scroll down to the mag_E1 field overlay that we created during the original Getting Started exercise, and we double-click on that to bring it back up. We'll hide the key again to make it easier to see. And now what we're going to do is select Animate to animate this plot against the position of the septum. So when we select Animate, we don't want to animate against phase. So we'll select New, and we'll set the sweep variable pull down to the variable offset. And we'll click OK. Now the software will regenerate the frames, one for each position of the septum, and generate an animation for us. And there you can see the effect of moving the septum from the center to the right of the screen, toward port 2. Now we can close this animation, and we're ready to move on to the optimization process. In order to perform an optimization on a variable, we must first make the variable available for optimization in the Design Properties menu. Selecting the Optimization radio button, we can include the variable offset in the optimization setup. In a problem with many variables, we can select subsets of variables to optimize against. After including the variable for optimization, an optimization setup is added in the project tree in the same manner as a parametric setup was created earlier. In the Setup Optimization dialog, we select the optimizer, specify the maximum number of iterations, and specify a cost function to optimize against. We will leave the optimizer and maximum iterations as the default, since this is considered a numerically non-noisy simulation problem. There is more on the selection of an optimizer and the number of iterations in the online help for your reference. To add a cost function, we click on Add in the cost function area of the dialog. We select the calculation text box and simply type in the function we wish to optimize against. In this case, we want the power at port 3 to be double that at port 2, or to put it another way, subtracting twice the power at point 2 from the power at port 3 should equal 0. I've typed this expression into the text field and pressed enter. The condition and goal fields complete the specification of the cost function. We'll set the goal equal to 0. The condition is already set to equals. And we'll set the weight value to the default of 1. We could use the weight to specify relative importance of cost functions in a scenario where more than one cost function is required, such as in a filter where the passband and stopband would have separate cost functions. We also need to specify a stopping criteria for the cost function calculation. This is the acceptable cost, and we'll set it to 0.1. The noise will remain at the default value. Moving to the Variables tab, we want to tell the software to override the starting value for the variable offset. We choose to start at the value we selected visually from the parametric sweep data in the previous chapter. We also set the minimum and maximum values for the variable, again based upon what we saw in the parametric analysis. Values of 0 and 0.3 seem to provide good boundaries around the design point we're looking to achieve. In the General tab, we specify two final aspects of the optimization setup. First, we tell the software to solve the parametric sweep before optimization. This allows the optimizer to select the best starting point for the optimization process. In this case, since the solutions are already completed, the optimizer will simply load in the solution data and use it to calculate the next solution point required without resolving the parametric sweep. Second, we choose Update Design Parameter Values after optimization to allow the optimizer to reset the basic design to the optimized variable values. Clicking OK completes the optimization setup, and we can right-click in the project tree and start the analysis. Now that the optimization process is complete, we will briefly review the results. Clicking on Optimization Setup 1 in the project tree and selecting View Analysis Result once again brings up the post-analysis display with the cost function calculation plotted. You can also review the results in tabular form. Notice that the optimizer includes the cost function calculation performed on the results of the parametric sweep for the first 11 iterations. Also note that on step number 14, the optimizer calculated a cost function below the stopping criteria of 0.1 and halted the process. Switching back to the table, we can see the final result as a value of the variable offset of roughly 0.9 as the optimum value for the power split we desired. Now let's close the results display and look at the fields for the final design. Since we asked the software not to save fields, a solution is not available to view immediately. However, since we asked the optimizer to transfer the final parameter values back to the initial design, the value of offset is already set to the optimized value. We can simply click Analyze in the base design and get the full field solution for the optimized T-junction. Just to show you, we'll select the T model, and you can see the value of offset is indeed set to the optimized value. Once the solution is complete, we can again review the fields on the top surface of the junction by double-clicking the plot that we have set up previously and allowing it to recreate the new data. To demonstrate a capability of HFSS version 9, I'll bring up the existing stored plot, and I'll hide the key. And if you watch carefully, when this simulation is completed, it will automatically update the plot. Now you can qualitatively see that the power being sent to port 3 is greater than that sent to port 2. This completes our example of parametrics and optimization. This was clearly a simplified example designed to demonstrate the use of the tool. Feel free to experiment with this very powerful addition to the HFSS system.